Okay, so it should be good now. So 6.2, radicals and rational exponents. So I don't really need you to write anything down initially other than the title. The first few things we're just going to kind of like talk about and review. If you did have the notes like printed, you can write them down with it. I'm not going to add too much to it from here. But just remember, so you might have learned what a rational number is before. It's just any number that can be written as a ratio of two integers. So a rational number, like I said, you don't need to write this part down. But a rational number in with this section is pretty much just referring to a fraction. So like 1/2 is written as a ratio of two integers, 1 to 2. Or like negative 3/4. Technically, any whole number is also a rational number because, like, say I have the number 5, I can write that as 5/1, or like any decimal that terminates or ends, that can be written as a rational number as well. But for the purpose of this section, it basically just means fraction. And then remember that a radical is just a symbol that we use to represent a root. So like you've probably worked with square roots before. That's just a regular radical. You won't see a number like outside it here or anything like that. It's just an assumed square root. For a cubed root, it looks pretty much exactly the same, except for you'll see a little 3 on the outside left of it, and that means that we're looking for the number that like multiplies itself 3 times to get to the number inside. Basically, radicals slash like roots are the opposites of like exponents. So like the square root would be the opposite of or the inverse of like raising something to the second power. And then same thing, like the cube root would be the inverse of like raising something to the third power. Okay, and then the next thing I need you to write is this second bullet point. So this is really, really important where it says to transition between radical form and rational exponent form, use either what we have written on the left or what we have written on the right. They have the same meaning. The only difference is that between the one on the left and the one on the right, this E is inside versus outside of the radical. Doesn't really matter which is which. It's just they're equivalent. There just may be some there just may be some problems that you would rather have the radical inside versus outside. But take a second to write these down, and then I'll kind of talk about what each different piece means. Okay, so really quick, I think my sharing is a little messed up, so I just need to stop sharing it and then reshare it really quick. Okay, so it should be fine now. If anything goes wrong or seems weird, just let me know. So if we're looking at these two different, like, I guess they're equations, but they're just kind of a way to help us remember, like, how to transition between what's called radical form and rational exponent form. So radical form is kind of what it sounds like. It's anything that has like a radical in it. And then rational exponent form is when we have something raised to like a fraction exponent. So if you see a problem that says like change from radical form to rational exponent form, you'll go from here to here. Or rational exponent form to radical form, you'll go from here to here. And then what each of the little, I guess, variables stand for is the b, like inside of the radical, that stands for base. And that just becomes like the base of the exponential, or like when you write it in rational exponent form, it'll become the base there. The R stands for root or index. You might see either word. So root or index, and then the E stands for exponent. And then to change it from radical form to rational exponent form, the B becomes the base over here. The exponent becomes the numerator of the fraction, and the root or the index becomes the denominator of the fraction. And then I don't need you to write these next 3 bullet points, but I'm going to just kind of read through them and talk about what they mean. So the first one, if R is odd, then B has one real nth root. So that means like basically if you're taking like a cubed root of something, then there's just one answer that you get out. Versus if R is even and the number inside the radical is positive, then there's actually 2 answers that you get out when you're solving. So for example, like if I were to solve an equation like x equals the square root of 4. Well, I think we all know that square root of 4 is 2, because 2 times 2 equals 4. But not only is it 2, it can also be negative 2. So like this would be x is equal to positive or negative 2, because negative 2 times negative 2 would also be positive 4. So either one works. But like I said, that's mostly just when you're solving. I don't really need you to focus a whole lot on writing both answers today, but when you do, I'll let you know. And then the last one, the nth root of a number may be a real or imaginary number. And this is a little typo right here, and I have to write it down. But the square root of -1 is equal to something we call I. And I just stands for this imaginary number, and it's defined as the square root of -1. So we won't work with I a whole lot in Algebra 1, but you will get into it a lot more once you get to Algebra 2. Okay, so example 1. This can be written down. So evaluating nth root expressions. So I'll give you a chance to write down the title, and then we'll start working through some of these examples together. Okay, so for A, the cubed root of -8. What that's asking is what number times itself 3 times is equal to -8. And depending on the number inside the radical, like how big the number is, it might be hard to figure it out in your head. There's some you certainly might be able to figure out in your head. But for right now, just know like we're going to be getting out whole numbers during this section, because this is really our first time like working with this stuff. So expect that your answer is going to be a whole number, like 2 or 3, 4, 5, 6, no decimals or fractions, at least for the time being. So if I were to take the cubed root of -8, if I wasn't sure what the cubed root of 8 or -8 was, I can make something called a factor tree. So that means I start with 8, my number, and I break it down until I get to its primes, or really all the factors I need. So like for 8, 2 factors of 8 would be 2 times 4. And then from 2, I can't go any further because that's a prime number. But 4 can be broken down into 2 and 2. So that means that if I were to take the cubed root of 8, since I made a factor tree and I got 3 2's, that means that 8 is 2 times 2 times 2. But since I'm taking the cubed root of negative 8, I have to incorporate the negative there. So it's not just going to be 2, it'll be negative 2, because negative 2 times negative 2 times negative 2, the first two negative 2's would be positive 4, times the third negative 2, 4 times negative 2 would become negative 8. So it's a good way to check that, make sure that you got not only the sign right, but you picked the right value as well. And then for B, this time it looks really similar, but this time the negative is outside of the radical, so it's negative and then times the square or the cubed root of 8. So for this one, we really don't have to worry about the negative. The negative is just going to stay out in front in our final answer. We just need to figure out the cubed root of 8. So it's asking what number times itself 3 times is equal to 8. Well, we just kind of figured that out right here, that 2 times 2 times 2 equals 8. So that means that the cubed root of 2 is 8, but we also have to bring down that negative. That negative just stays out in front. And then, sorry, I think I said that backwards, but the cubed root of 8 is 2. So negative 2. So the difference between A and B was that because we were taking the cubed root of a negative number, we needed a negative multiplied 3 times to get that negative inside the radical. For B, we're just taking the cubed root of a positive number, but there's a negative out in front, so a negative just gets brought down. Okay, and then for 16, here's where it's really very, very helpful to be able to change from rational exponent form, what this is in now because we have a fraction exponent, to radical form. Because a lot of the time, maybe always, like rational exponents, it's hard to make sense of them, but once you see them in radical form, it becomes easier. So to change from rational exponent, which that just means a fraction exponent, so b raised to the e over r, I put the b inside of the radical. The r, the denominator of the fraction, becomes the root or the index, and then that gets raised to the e power. So for C, like 16 to the 1/4, the 16 is the b value, the 1 is the e value, the 4 is the r value, just like comparing where each one is up here. And then if I want to write that in radical form, the 16 will go inside the radical. The r becomes the root. So in this case, r was 4, and that's being raised to the first power. But remember, anything that's being raised to the first power, we don't really necessarily need to write it. It won't really affect our final answer. So this is really just the fourth root of 16, and now we can figure out what the fourth root of 16 is. So the fourth root of 16 is asking, like, what number times itself 4 times equals 16? So you may be able to figure it out in your head. If not, you can always make a factor tree. So like 16, two factors of 16 can be like 2 and 8 or 4 and 4. And then we're taking the fourth root. So we need 4 of the same number, not just 2 of the same number. So 4 can break down into 2 times 2. And then this 4 can also break down into 2 times 2. And we were looking for the fourth root. And on my factor tree, I ended up with 1, 2, 3, 4 2s. That means that the fourth root of 16 is 2. What this factor tree is saying is basically 2 times 2 times 2 times 2 gets you back to 16. And then for D, so negative 16 raised to the 1/4 power. Same thing here, like the rational exponent, the fraction exponent is confusing. So we want to change it to radical form. In this case, the negative 16 is the b, and the negative has to be included because it's in parentheses. And then the numerator of the fraction, the 1, is the e, the 4 is the r. So if we change it to radical form, the negative 16 goes inside the radical. And then the 4 becomes my root, and the 1 becomes my exponent. That 1 doesn't really make a difference, so we really just need to try to figure out what the fourth root of negative 16 would be. And think about this. So the fourth root of negative 16 is asking what number times itself 4 times equals negative 16. So we just figured out that the fourth root of 16 was 2. And so think about whether or not it makes sense for like the fourth root of negative 16 to be negative 2. Think about what happens if I take negative 2 and I multiply it by itself 4 times. Do I end up with negative 16? So if I test it out and I check to see negative 2 times negative 2 times negative 2 times negative 2, so negative 2 to the fourth power, these two negative 2's, negative 2 times negative 2 equal positive 4, because a negative times a negative is a positive. And then if I do 4 times negative 2, that's negative 8. And then times one more negative 2. So negative 8 times negative 2 is positive 16. So the fourth root of negative 16 doesn't actually, not that it doesn't exist, but it's not a real number. So it's kind of going back to that imaginary number thing that we talked about up here. You don't have to worry about it too much. Like I said, that's something that you'll get into in Algebra 2 more. But if you're ever taking the even root of a negative number, so like we're taking the fourth root of negative 16, you can stop there and say not a real number. Because it's not a real number, it's technically an imaginary number. And then if you want to leave yourself a note as to why, it's because you're taking the even root of a negative number. Okay, and then we have 2 more examples to go through all together and some for you to practice on your own, and then we'll be done for the day. Okay, so for A, I'll give you a chance to write it down, but it's 16 to the 3/4 power. So whenever you're given something that has a fraction exponent, it's usually smart to change it to a radical just to make sense of it, because the rational exponent doesn't have a ton of meaning unless like somehow you get super comfortable with them really quickly. So for 16 to the 3/4 power, the 16 is my B value, the 3 is the E, and the 4 is the R. So if I want to rewrite this in radical form, the 16 goes inside of the radical, the 4 becomes the root or the index, and then that's being raised to the third power. So what this is saying, it's not saying you have to do it all in one step, it's saying that we need to figure out what the fourth root of 16 is, and then once we know what it is, we can raise it to the third power after. So up here on like example C, the 16 to the 1/4, on that problem we figured out what the fourth root of 16 was. So the fourth root of 16 is 2, because 2 times 2 is 4, times the third 2 is 8, times the fourth 2 gets you to 16. But then we still need to take that 2 and raise it to the third power. So just to recap that, when we take the fourth root of 16, we get 2, but then we still have to raise that 2 to the third power because of that 3 exponent over the radical. And then the 2 to the third power just means 2 times 2 times 2. So 2 times 2 is 4, and then times the third 2 is 8. So that means that 16 to the 3/4 power is equal to 8. And then for b, we're going to go about it a similar way. So same thing, we have a fraction exponent, which is kind of confusing. So we're going to try to change it to a radical. So the 27, that's b. The numerator of the fraction, that's e. And the denominator of the fraction, that's r. So if I want to rewrite it in radical form, the 27 goes inside of the radical. The r is the root of the index, so in this case, that's 3. And then that's being raised to the 4th power. So what this is saying is that we have to figure out what the cubed root of 27 is, and then once we figure it out, we can raise that number to the 4th power. So the cubed root of 27, it means what number times itself 3 times equals 27. If you can't figure it out in your head, like I said, that's perfectly fine. You can always make a factor tree to help you. So if you start with 27 and then break that down, 27 we know is 3 times 9, and then 9 we know is 3 times 3. So since we're taking the cubed root, we're looking for 3 of the same number. So we have 3 3s at the end of our factor tree. That means that the cubed root of 27 is 3. And that makes sense because 3 times 3 is 9, and then times the third 3 becomes 27. But we still have to raise that 3 to the 4th power. So if we want to figure out what 3 to the 4th power is, that means 3 multiplied by itself 4 times. 3 times 3 times 3 times 3. So we end up with 81. Okay, and then your practice problems are up there now. So there's those 4. I'm going to give you guys a few minutes to work through them, and then we'll go through them all together. Just remember, for anything that has a fraction exponent, so like b, c, and d, you're going to want to try to change it to radical form and get comfortable with that. So I'm going to rewrite it up here. I would recommend like writing it on your notes, writing it on like your homework assignments, just so it's like right there so you can see it and you don't have to like put in the effort to go and find it. So that's b raised to the e over r equals the r root of b to the e power. And then just one more note before I stop talking and leave you guys to start working. You only really, not only, but like for the most part, you're only going to want to go from like rational exponent form to radical form. Like, so for a, you don't need to change a to like rational exponent form. You can just leave it in radical form and evaluate it there. About a minute left, and then we'll go through them together. Okay, so if we look at A, it's the cubed root of negative 125. So that's asking you what number times itself 3 times equals negative 125. Well, the first thing that we know is in order to get a number, a negative number from multiplying 3 numbers together, is that number has to be negative, or the number that we're multiplying by itself must be negative. We just have to figure out what that number is. So some of these, like, just like how when you were learning about like perfect squares, like, and square roots, like the square root of 9 is 3 and the square root of 25 is 5, you may start to remember a lot of like these perfect cubes or like fourth root numbers or and everything else. But if not, just remember you can always do a factor tree. It's an option. I'm going to show you like the factor tree for almost every problem. Just know if you don't need it, you don't have to use it. It's just kind of like a backup that if you understand it, it's helpful. It's there for you. So if I'm not sure what number times itself 3 times equals 125, set up 125. And then I know that anything that ends in a 5 is divisible by 5. So if I do 125 divided by 5, that leaves me with 25. So I know 5 times 25 must be 125. And then if I know that 25 breaks down into 5 times 5. So since I'm taking the third root, I want 3 of the same number at the end of the factor tree, and I got 3 5s. So that must mean that the third root or the cubed root of 125 is 5. But since we're taking the cubed root of negative 125, I have to make all those 5s negative to get to a negative product. So the cubed root of negative 125 will be negative 5. And just remember like how easy it is to kind of check your work for these problems. This is just saying that negative 5 times itself 3 times will get you back to negative 125. And you can definitely like check that pretty quickly. Like negative 5 times negative 5 times negative 5. The first two negative 5s multiplied together becomes positive 25, and then positive 25 times negative 5 becomes negative 125. So we get back to the number that was inside of the radical. And then for B, so for negative 64 to the 2/3 power, we have a rational exponent, so we want to change it to radical form. So this negative 64, that's my B value. The 2, the number in the numerator, becomes the E, and the 3, the number in the denominator, becomes the R. So the negative 64 goes inside of the radical. And then the 3 becomes my root or my index. And then the 2 becomes my exponent. And I don't really need to worry about the exponent until my very last step. My main focus is figuring out what the cubed root of negative 64 is first. So if you can figure it out in your head, more power to you. Just remember, I'm going to show you a factor on each one. This one's a little bit more complicated, and I'll show you why, obviously, in a second. But just know it's still something that you can use. So if I want to make a factor tree for negative 64, or I'm just going to focus on 64 for now, and we'll worry about the negative after. I know that 64, it can break down into, let's say, 8 times 8. And then 8 and 8 break down into 2 times 4. And then this 8 breaks down into 2 times 4 also. But then the 4s can get broken down further into 2 times 2 and 2 times 2. So when we look at a factor tree, we usually use like what's called the leave, so like the end of it. So like the 2, 2, 2, 2, 2, 2. And what's tricky here is I am taking the third root of something. So usually that makes me want to look for like the any number that I have 3 of. But you can see I have 1, 2, 3, 4, 5, 6 twos. So I have basically like groups of twos, like 3 pairs of twos. So I think I have 1 pair of twos, another pair of twos, a third pair of twos, and each pair of 2 is just representing like 2 times 2. So really each pair of 2 is 4 times 4 times 4. So that means that the cubed root of 64 is 4. 4 times 4 is 16, times the third 4 becomes 64. And then because we're taking the cubed root of negative 64, that must be negative 4. But like I said, this like whole factor tree thing, it's just a skill like that you should have in your back pocket. If you don't need it or if it's confusing, don't worry about it for now. And then the last thing that we need to do is go ahead and just raise that negative 4 to the second power. So negative 4 to the second power means negative 4 times negative 4, which negative 4 times negative 4 will become positive 16. So since the negative was in parentheses, it gets squared along with the 4. So that negative times a negative cancels out and becomes positive. And then for C, so 9 raised to the 5 halves power. We have to take this and rewrite it in radical form. So the 9 is my B, the 5 is the E, the 2 is the R. So the 9 goes inside of the radical, the 2 becomes the root, and then the 5 becomes the exponent. So that means that I have to take the square root of 9. Once I get that, I'll raise it to the 5th power. So the square root of 9 is 3, but that still has to be raised to the 5th power. And then 3 raised to the 5th power means like 3 times 3 times 3 times 3 times 3. Do that, you can use calculator always, but you end up at 243. And then for the last one, for D, 256 raised to the 3/4 power. Same thing, we want to rewrite it in radical form. So the 256, that's my B. The 3, that's my E. The 4, that's my R. So if I rewrite it in radical form, the 256 goes inside of the radical. And then the 4 becomes the root, and the 3 becomes the exponent. So I have to find the 4th root of 256 and then raise that to the 3rd power. And honestly, like with these problems, I'm telling you, like, I'm not going to give you like 4th roots or 3rd roots that end up being like crazy decimals or anything. So you can also kind of like guess and check, to be perfectly honest. Like if you think maybe like 3 to the 4th power would be 256, or the 4th root of 256 should be 3, you can test it out by like actually multiplying out like 3 times 3 times 3 times 3. That's 81, so that doesn't work. Or you can test out like 4 times 4 times 4 4 times to see what you get there. Well, 4 times 4 times 4 times 4 is 256. So that must mean that like the 4th root of 256 is just 4. So you can guess and check. You don't have to. There's lots of other ways to do it. I'll show you the factor tree as well in case like it's helpful for anybody. But if I were to make a factor tree for 256, it's going to be a big one because it's a big number. But 256, if you're not sure, you can start with like an even number. So it's even, so we can divide it by 2. So 256 can break down into 2 and 128. And then 128 can break down into 2 and 64. And then 64 can break down into 2 and 32. And then 32 can break down into 2 and 16. I told you it'd be a big one. And then 16 can break down into 2 times 8. 8 can break down into 2 times 4. And then 4 can break down into 2 times 2. And since we're looking for the 4th root, we're looking for 4 the same number. We obviously have definitely more than 4 twos. But it looks like we have 1, 2, 3, 4, 5, 6, 7, 8 twos. So if we have 8 twos, then we technically have like 4 pairs. 1, 2, 3, 4. And just remember, these are all factors, so all just being multiplied together. So each pair of 2s means 2 times 2 or 4 times 4 times 4 times 4. That means that the fourth root of 256 is just 4. And then that still needs to be raised to the third power. So we have to take that 4 and multiply by itself 3 times. So 4 times 4 times 4. And then that leaves us with 64. So that was the last example for today. We're going to start transitioning to Delta Math. I'm going to leave this screen up for a little bit just in case anybody was still writing anything down. But if you want to head to Delta Math and start working through it, you can.